Okay, so we are very happy to have Alex with us today, and Alex Buchel he's going to talk about stabilization of the extended horizons, something new as far as I understand, brand new. So thank you very much, and go ahead, Alex.
Thank you so much, Matthias. So I want to thank you guys all for keeping this thing running. So I have been enjoying it for, this last year or so. And I feel hopefully I can entertain you a little bit and pay back for the efforts you did. So I'm going to talk about this stabilization of extended horizons. Let me start by saying that please interrupt me at any time and, ask questions. And so this is something that in the process of being posted, so it's maybe 1/3 written, so it should soon appear. Good. So let me start. So when you open Landau Lifshitz, this is volume 5, so there is a nice chapter, thermodynamic inequalities. It's chapter 21, I believe. And so one of the conditions, if you have a thermal equilibrium state, then one of the conditions that this quantity has to be positive. So usually we have a positive entropy. And so this translates into the statement that the specific heat at a constant volume has to be positive. Okay. And so this statement, it's known as condition for thermal stability, equilibrium thermal stability. Now, in these talks, we all like to use gauge theory, string theory correspondence. And so we all know that black holes and black brains, so in equilibrium, they are dual to thermal equilibrium states of our holographic field theory. And so typically when a GR person talks about holes or brains, so the things that comes to mind are whether or not the corresponding object stable. And the things that we look at are the quasinormal modes, right? So we compute the spectra of quasinormal modes. And so what I have done, I represented the frequency and momenta of the quasinormal modes, and a familiar condition for the stability of the quasinormal mode is that the imaginary part of the frequency has to be negative. So there's just a statement that when this quasinormal mode is excited, it decays exponentially with time. So are there any questions? No. Okay, so let me go ahead. So in early 2000s, there was a nice series of papers by Steve Gopse and Mitra. And so what they formulated something that has been known as a correlated stability conjecture. And so this correlated stability conjecture is a statement that basically the thermodynamic and dynamic stabilities or instabilities, right? So probably a better way to put these things in quotation marks, right, are actually correlated. And so there were several important things that went into this conjecture. So the first one is that there should be translational invariance of the horizon, right? So that would be black brains, and that would be a holographic dual to some boundary gauge series in Minkowski spacetime, for example. And so in particular, you can prove that Schwarzschild black holes are stable. So in particular, the formalism that I will review can be used to prove this statement. And that's actually, so we're talking here about vanilla Schwarzschild black holes. So there is, just no chemical potential, no charge, no non-rotating, no scalars, all of these things. And you can prove this statement in arbitrary dimension. Right, so this issue of translational invariance of the horizon appears to be crucial. And so when we talk about, so I use the word dynamical stability or instability, and so in particular this instability is just a statement that you can identify a quasi-normal mode of the type like this. So once excited, it actually will bring inhomogeneities to the translational invariant horizon, right? So I will use maybe later the word crumpling. Very good. So are there any questions? Yep. Okay. Okay, so this is a conjecture.
Alex?
So, yep.
Alex, may I interrupt? Hi.
Yeah, please, anytime.
Why is translational symmetry crucial? Couldn't we find stable states that are not translationally invariant? What would be wrong with those?
Right. So that's a very interesting question. So over here, what I wanted to emphasize that it's translational invariance versus, so basically black holes versus black brains. So not in the sense that you look at some funny equilibrium states that where translational invariance is spontaneously broken or explicitly. Okay, and you look for basically thermal states of that type. So it's an interesting question. I don't have much to say here. It's just a statement. I want to emphasize that black holes are actually stable. Okay.
So Alex,
yeah.
Sorry, one more question since you already got interrupted. So presumably, well, two things. Presumably, in addition to translation invariance, you want to require non-compactness because you could have, a black brain compactified on a torus, and then some unstable modes wouldn't fit.
Yes, I agree with that. I agree with that. But as so as you will see, I'm not trying to advocate in the next two transparencies. I'm basically will not be advocating that.
Okay.
But let's get Go ahead.
Yeah, the other thing is when you talk about quasinormal modes, do you include also? I mean, do you mean just proper quasinormal modes or also hydrodynamic modes?
I would. For me, hydrodynamic mode is also a quasi-normal mode. Yeah, I'm sorry, it's probably abuse of language. So I will bundle them, and it will be actually important because as I will show you some nice pictures, what happens with the what I call flow of the quasi-normal modes. As I start changing something, you will see that things get changed. What was hydrodynamic becomes non-hydrodynamic, and so I think it's important to actually keep the big picture.
Okay.
Especially, we know that we talk about hydrodynamics only when we are non-compact, right? So at vanishing frequency. And once I start talking about curved horizons, which is exactly where I'm heading to, so those things will become opaque, to say it best.
Thanks.
Okay, very good. Thank you so much, guys, for asking questions. Good. So let me go and talk a bit about this conjecture. So I would say that in one direction, this conjecture is trivial. So what I have done here, I have taken this Landau-Lifshitz condition and I took the inverse of it. And it just turned out that this ratio of entropy density to the specific heat is the speed of the sound wave squared. And so now you can clearly see that when you have a negative specific heat, that also implies that the speed of the sound waves squared is negative, which means that the sound waves are purely imaginary. And so now when you look at the familiar dispersion relation for the for the sound waves, so you can see that so I wrote two terms in the gradient expansion, and you can see that the first term, which is plus or minus the speed of the sound waves, it's plus or minus I times Q. And so you can see that at least for some sign, and as long as Q is small enough, meaning that you can neglect these corrections, you actually expect an instability. So one other comment I want to add is that if you look at least at these first two terms, right? So let me be fancy and highlight them in a different color. So if you look at those two terms, so they are purely imaginary. So typically, when we talk about a sound wave on an extended horizon, so that's a propagating mode, right? So we talk about real speed of the sound waves, and so over here, when you look at the first two terms, that's an indication that this is in this regime. The sound mode becomes a quasi-normal mode, which has purely imaginary dispersion relation, and you cannot conclude really that it's purely imaginary, but then we will see that that's really the case. So sorry. So what I'm trying to say is that over here. So this would be the branch of the quasi-normal modes where the real part vanishes. Okay. So are there any questions at this stage? No. Okay. Good. So I said that there is this conjecture, and so in one direction it's trivial, and so in the other direction the conjecture is simply incorrect. Okay. So there are various ways at different level of rigor how you can look of this. And so what I'm going to mention something that in some sense inspired what I am talking today, which is a holographic conformal order. And so in particular, I want to show that the thermodynamic stability does not imply a dynamical instability. So in other words, this will be yes, and this will be no. Okay. So let me give you a very quick review of the what I call holographic conformal order. I'm not going to go into lots of details, and because that's a completely different talk. So the point is that it's straightforward to construct holographic models, right? So you can, it doesn't matter, it's ADS4, ADS5. And those models say can have some global symmetry, right? So this is also not important. The class of model is really huge. And so what's important is that you have some toy holographic models that you play with. So you construct your Schwarzschild-like black holes. There will be some scalar hair in that black hole. And then you study thermodynamics. And so when you study the thermodynamics, you will discover that there are two phases of your conformal field theory. So it's important that the models that you are talking about is CFT, so that if you have some scalars, those scalars cannot have non-normalizable modes turned on. And so as typical for conformal field theory, so when you look at the, for example, free energy, when you make a dimensionless ratio where you use temperature as the other scale, you will find out that there are two phases, one where the Z2 symmetry is unbroken, and the other phase, which makes actually, in my view, this conformal order thing very interesting because it violates no-hair theorem. So you sort of have a you have ADS-like black brains, and there is a scalar hair outside. So that's this here is characterized by this constant kappa, right? So this constant kappa in the examples that I know, it's between 0 and 1. So now, so that's it. So the phase, the two phases are very simple, and you can immediately conclude that the thermodynamics, both the thermodynamics and the hydrodynamics of two phases is identical. Okay, so you can go and do complicated computations for, say, for example, in this phase, what would be the speed of the sound waves? Is the bulk viscosity still vanishing? Those and non-trivial looking questions, since you have bulk scalars present, but you will find out, yes, you know, the speed of the sound wave squared is 1/3, as you expect. In case of ADS5, bulk viscosity vanishes and all of that. So those are genuine thermal backgrounds dual to thermal states of CFT, and you know they are obviously thermodynamically stable. However, and so when I found them in a holography, I was very excited. However, unfortunately, what you will discover that there is a quasi-normal mode. There is something that you could not have foreseen from from thermodynamics alone. And so on that branch, there is an unstable quasinormal mode, right? So there is a quasinormal mode with this condition. And so what happened with your hair is that it is just basically perturbatively unstable. Okay, and so this, in my view, is a cleanest example why this correlated stability conjecture is not true. Okay, so are there any questions? So I don't really care about the correlated stability conjecture.
Sorry, Alex.
Yeah.
When you say the thermodynamics is identical, also the free energy is the same for both phases?
No, that's not. If you look at this, okay, so let me, right.
I mean,
so the free energy is not
so
the same, otherwise it will not be the same phases. If you look at these formulas, the ones that I'm erasing, right? So let me again. So you see the constant over here is the same, right? So this constant is proportional to the central charge. This is like your familiar n squared.
Yes, yes.
And then it's multiplied by a constant, right? And so the two phases are different by this constant, right? So it's a conformal field theory. So there are no other scales other than temperature. So the free energy cannot, if I take the free energy, for example, when I talk about CFT4, so if I take a free energy and divide by T4, that has to be a dimensionless quantity. It has to be a constant, okay? And what I'm saying is that the two phases basically differ by what this constant is.
Okay.
So over here, this is your vanilla ADS Schwarzschild.
Mm-hmm.
And so this is the one that has hair. Okay, so that would be a very interesting object because it would be a Schwarzschild ADS black hole with a hair.
Yeah. But yep. No, go on.
And pretty much because of that, that's a constant. You can see that the thermodynamics is exactly the same, right? Because it just overall constant as far as it concerns the free energy.
But then you find it's unstable and
right. So this is unexpected because normally, well, I have been writing some papers over the years about this Gopsi conjecture, but deep inside, I still believed it's kind of okay. And so I thought that, I keep studying those models because, that's, if you wish, a new state of matter, right? So let's just explore it, something that holography screams at us. And I was very upset when I found this unstable mode. So it's a non-hydrodynamic mode, right? So it's basically, if you were to plot it, right? So this is a real part of omega, and this is an imaginary part of omega. And so what you will find out something like this picture. So
shouldn't we have expected that there's going to be an instability since the free energy for your broken phase is higher than for the unbroken phase?
That's no, I wouldn't, right? But it's a good observation, right? So just looking at the free energy, I see that that this broken phase, right, or this phase with a hair is metastable at best, right? But that does not necessarily mean that. And so, for example, you're absolutely correct. What you are saying is that this phase is not dominant in canonical ensemble.
Because let me ask it differently. Then
no, but
if you were able,
let me. I'll come back to you in a sec. So I know examples where this happens, but then the phase that is subdominant in a canonical ensemble becomes dominant in a microcanonical ensemble. And so if it would be like that, if it would be sort of, okay, so this phase is like some ridiculous phase that is never realized physically, this is not the case. So there are exactly examples like this that happens. And the one that is closest to me are Klebanov-Strassler black holes. Those are, so Klebanov-Strassler black holes do not dominate in a canonical ensemble. Their free energy is bigger. However, they are more entropic. at the same energy density. And so they dominate in the microcanonical ensemble. And so what this means is that if you were to do a simulation, right, how does your system evolve? You don't really care about, you know, canonical ensemble. It's the microcanonical ensemble that determines how your system evolves. And so those issues are actually important. The only, if you wish, the only imprint of this stuff that happens is that this crumpling instability. So this, if you have this thermodynamic instability, which is an instability of the canonical ensemble, it shows up in the microcanonical ensemble through the instability in the quasi-normal modes. Now, please go ahead, and I interrupted you, sorry.
Because I was trying to think in analogy to holographic superfluids, where you see the instability because there's a mode over the normal phase that does have this QNM with the wrong sign for the imaginary part. Here, I would imagine that you need something that goes the other way around.
Yeah, so those are the ones that in my papers we kept calling it exotic black brains, right? So that they behave, for some weird reason, they behave in a completely opposite way from the holographic superconductors, right? So as you pointed out in the holographic superconductors, what happens is that this broken phase usually exists at low temperatures. And so here, this would be in a canonical ensemble, this would be the phase that exists sort of at high temperature instead of low temperature. So you develop hair as you go above certain critical temperature rather than below critical temperature. So that's very unusual. You might think, oh, he is crazy. But in fact, you know, this thing we discovered in a holography years ago. And then there was a recent paper by Zohar Komargovsky and company, and they found exactly the same phenomena in quantum field theories. And so my interest in that got resurrected. Okay. Right, very good. So let me go on. And so hopefully I try to convince you, that that's an interesting type of questions. And I told you what's my motivation to look at that. And so what I'm going to do in this talk, I will try to fix this instability, right? So it shows up in, as I mentioned, in various interesting examples. And the only way so the straightforward way I thought I could fix it, I still don't know if I can in the well, you'll see. So it's just basically taking your black brain and turning it into a black hole. So I'm going to introduce a curvature of the horizon, right? So now my translational invariance, I replace it with a sphere. And so the sphere will be characterized by the curvature scale K, and that's just 1 over L squared. And so, as I said, the motivation, this already came up. So one motivation is to understand these Klebanov-Strassler black holes, which have lots of applications. And the second one, that once I write down this paper, that's what the next one will be about. It's basically exploring this holographic conformal order when I compactify it on the sphere. And so the motivation here is to fix the instability in this funny of this funny state and see whether you will destroy conformal order before you fix the instability. So that's kind of the question that that I'm very curious about. Okay. So that was kind of an introduction. So the outline of the rest of my talk. So what I will do, I will present the general formalism for the quasi-normal mode. So it's basically some overview plus generalization of what's known in the literature. And then I will talk about the application, which is n equal to star model.
Excuse me, can I make a question?
Yeah, absolutely.
Yeah. So the setup you just talked about, like the higher free energy in microcanonical ensemble, and I've seen that kind of situation in super radiant instability of black hole. So do you think this situation is like for small black holes?
I will be like Bambi. If I have something nice to say, I will say nothing at all. I'm just joking. I don't really know, seriously. It's an interesting question. And the good thing is that the framework I will describe, you can really address this question.
Mm-hmm.
So
Thank you.
Good. So let me go. So most of you are familiar with the formalism of Kovtun and Starinets for computing the quasi-normal modes. And basically the way how it goes is the follows. So you form gauge invariant fluctuations. There will be different sectors. One that brings our familiar shear viscosity and its universality. Then there is a helicity 1 sector, helicity 0 sector. So that's where bulk viscosity and sound mode is. So you form this, this gauge invariant fluctuations. You derive, equations of motion. You impose an incoming wave boundary condition, and so what you do after that, you solve them and you determine your spectrum. And then there is a lot of very beautiful talks on this holotube where you discuss applications of this method. Okay. So this is something that I want to emphasize typically numerically. So a lot of progress, in particular in regards to the shear viscosity, was done that a lot of things you can do analytically. Okay. I want you to keep this in mind analytically in a hydrodynamic limit. So that's real beauty. Good. So this is what I just mentioned. So there are some advantages of this Kovtun-Starinet. So in my view, it's very intuitive and straightforward. And so that's what I said, that this hydro limit can be treated analytically. And it actually, in my view, that was the reason that all these activities that led to non-equilibrium, eventually chaos and all of that started. Because you have an analytic handle in the framework of Kovtun and Starinets to compute the quasi-normal modes. So there are some disadvantages. Well, unfortunately, they are not suitable in my case when I want to look at the spheres. So something that I did not appreciate is the fact that it's actually that formalism is not suitable if you are in a business of proving stability theorems, right? So what I mean by that, can you prove in general that, say, in this system, once you construct the black hole will not have unstable quasi-normal modes? Okay, so that's a deep question. And there is a reason for that. Sorry. And so the reason for that is it's not a technical reason. I would say it's a conceptual reason. And the reason is that if you look at the equations, then both the frequency and the momenta in these quasi-normal mode equations enters in a highly nonlinear fashion. And so I would say that from that equation, proving a condition that something like this for all quasi-normal modes is just impossible. It's just, it's just a mass due to the nonlinearities how those things appear. And of course, there was a world before Kovtun and Starinets, and so which I personally did not appreciate because I lived in the hydrodynamics. And there were nice papers by Kodama and Ishibashi. So this is a review that I'm referring to, So the title of their paper is a master equation for gravitational perturbations of maximally symmetric black holes in higher dimensions. So what they did here is basically only ADS Schwarzschild-like black holes. And so there was an important, once I knew what I have to do, I explained to you the motivation. Then what I did, I went on Inspire and I started looking, I hated to develop the formalism. And so I started looking what other people did already in computing the quasi-normal modes in this approach. And I was very happy to discover the paper by Andrei Rostvorovsky and company. So what they did, they basically took the Kodama and Ishibashi, and then what they did, they added a single bulk scalar. Okay, so I thought it's a great start. it's not exactly what I mean, because often the systems that I'm interested in have multiple scalars, but it's a good start. So what are the advantages of this new approach? Well, I mean, to begin with, that's exactly what we need. Okay, so so the second thing that is crucially different from Kovtun-Starinet's approach of computing quasi-normal modes is that those equations are non-linear in Q, but they are at most quadratic in omega. So you will see this in a little bit. And so it turns out that this thing is super important. And you can actually prove, you can leverage this to prove that there can never be instabilities in this helicity 2 and helicity 1 sectors, right? So those are the sectors that were shear mode, tensor fluctuations. And this is a proof, you know, just k equal to 0 or k is positive, right? And so the statement is that if the instabilities in the quasi-normal modes exist, they can only be in the scalar channel, right? Something that is sound waves. And so I thought that it's very, very cute. Okay, and actually that's the route how you prove that the ADS-Schwarzschild black holes are stable, right? Because in that case, you can actually extend the theorems. You can actually extend the theorems for the high helicity sectors to the H equals 0 sector for the ADS-Schwarzschild. Okay, so that's the advantages. That's the advantages of this approach. You know, I would encourage you to look into it if you haven't done this before. However, there are some shortcomings. The one is that, as I said, I would need to generalize it to many scalars. So the second one, I could be wrong, but I spend a lot of time with it. So I believe that the statement is correct. So so we still need Kovtun and Starinets and all that stuff. And the reason is that that if you look at these sectors, the equations are singular in the limit Q goes to Q equals to 0. So you can still handle it analytically, okay? So you can basically take the hydro limit. You just cannot put Q equal 0 right away. So one way to see this is that the limits Q goes to 0 and are going to the boundary. And you need to impose on quasi-normal modes boundary conditions at the horizon and at ADS boundary. And so those two limits do not commute. So in particular for the, okay, so I made a typo here. I have many typos, especially in the previous version of this, so sorry. So in particular, if you start looking at the sound waves, okay? So what I'm telling you is that all these beautiful things, the statements that we can analytically compute shear viscosity and something, I simply do not see how it's possible to do it in this framework, okay? Now, the second thing that was, you know, I was a lazy person and I thought all I will do, I will simply take their formulas. So yeah, they use a different gauge and things like that. But I'll just borrow their results and start applying them to what I care about. And it took me almost 2 months to actually figure it out that I just have to forget about their paper. So they have all the right words, they have very clear presentation, but their formulas, you know, in this business, the factors matter. Okay, the factor of 1/2 and things like that, that's what you were dealing with. And so there were extremely many typos, and so I basically had to rederive everything. So that will be in the appendix of my forthcoming paper. And so let me just overview for you what will happen and just highlight some of the advantages. So, so I will look at the effective action of this general type. So there will be basically an arbitrary number of scalar fields. So P is the number of the scalar fields. So that's a normalization of the kinetic term. So those guys, eta, J are constants. And so the formulas that you will find for the quasi-normal modes going to be for the effective action where this potential is arbitrary. So I don't really care how nonlinear and how those scalars interact. So the formulas are still correct. And so another thing that I think is useful that distinguishes if you want to apply the formalism compared to Rostvorovsky and company paper is that I will present the results when the black brain or black hole metric has this particular form. So in particular, all my formulas will be C1, C2, and C3, and I don't really care. As long as it satisfies the background equation of motion, I will express the final formulas in terms of these warp factors. And that's very useful because, you know, sometimes you find that one particular parameterization of background suited you better than the other one. So very good. And so what you see here that I will discuss in kind of in one way both black holes and black brains. So those are the compact, well, they can be compact, non-compact, so you can have whatever horizons you want. And so there is an explicit presentation how you can think about the metric on different curvature maximally symmetric spaces, x3, comma k. So this, for example, this metric is secretly a sphere. And so the way how you can think of this as being a sphere for positive k, if you start introducing coordinates like that. So I'm going to pause here and ask the question is, you know, is sort of the class of models are clear to everybody? Okay. All right, very good. So so then I will focus mostly for spheres, right? So, but again, I want to say that the formalism is applicable equally to k equals 0 or k negative. And so,
sorry,
so I do not
want to.
Yeah, please.
Sorry. So you don't care about the, you said arbitrary potential, so you don't care about the dimensions of the scalar? I mean.
Well, you have to be careful, right? So the formulas that I will write, it doesn't matter, right? So it can be a scale of any, you know, conformal dimension, if that's what you're asking. You have to be careful what kind of boundary conditions you will be imposing. So I will tell you what the equations of motion for the quasi-normal modes are, okay? And then once you solve it, you have to do exactly the same as in Compton-Starrett. You have to impose correct boundary conditions. And yes, the answer to your question, I don't. So okay. So I'm solving all the problems for you with the equations of motion. Okay.
Thanks.
Yeah. Sorry, Alex. Can I?
Yep.
So the scalar fields can have a source in your case, right? Or you still want to have
yes, okay. They can have source. So this model is not CFT. Okay, so it's not a conformal theory. So you can have, you know, you can have masses. And so the examples that I'm going to talk about, n equal to star holography, where I am going to apply all of this machinery, it has a mass term. Okay.
Thank you.
All right, very good. So, what I wanted to say is that I do not want to in any way diminish the work done by this gentleman, and in fact, let me say that without their work, I'm not sure, you know, it would have taken me probably a year. I was getting more and more upset until I discovered that paper, and so that paper was crucial. And once you know the right words, right, so it's very easy to do the right formulas. Okay, good. So the idea now we have to basically repeat everything that Compton and Starrett did. And again, this was done in it's not, I did not invent this. So let me go straight. And so again, my contribution is just multiple scalars and arbitrary parameterization of metric. So you can organize the fluctuations again in the helicity sets. I'm not going to go into technical details. If you, it's not it's not worth discussing in this setting. You can look at paper later, but I just want to emphasize some subtle things. And so some things that that you might miss on the first reading of Rostvorovsky paper or my paper. Okay, so the general, so now I'm talking about fluctuations. So these capital Phis, they will be fluctuations. And so there will be a part that depends on the radial coordinate and time, and then there will be an angular part, right? So depending, so those will be the wave function on, on your maximally symmetric space. And so those will be familiar plane waves when you have a planar horizon, or they will be spherical harmonics, right? So in this case, I'm talking about S3. And so there will be a particular, a particular spectrum. So for planar horizon, K can be anything, and for spherical harmonics, it will depend on L. Now, so you have to be aware that once we talk about harmonic analysis, so there are scalar harmonics, then there are vector harmonics, and then there are tensor harmonics. It's just about when you discuss fluctuation, and they are very different. So for example, if I would write down basically their eigenvalue, eigenfunction, so what I wrote for the scalar harmonics. And when I write down for the vector harmonics, then there will be minus K here. So it will be something like this. That's what the eigenvalue, eigenvector equation will look like. And for the tensor harmonics, it will be even more complicated. So it will be K squared. Well, I mean, at least the equation will look, but there will be lots of indices. Okay, I'm suppressing lots of indices here. And so when I talk here, so those are actually, you need to decompose using the tensor harmonics. And so you need to decompose here using the vector harmonics, which are different objects. As far as you look at the fluctuations, so those are really different objects. Now, once I start talking about the equations, which I will in a second, so there is a universality in these equations, and universality is in the sense that I don't really care whether it comes from these complicated tensor harmonics. I will always rewrite the equations using the scalar harmonics. Okay, so this was probably not very clear in Rostvorovsky and company papers, but that's the way how the formulas work. Okay, and now the punchline. So it turns out that the equations, once you write down the equation, they're incredibly beautiful and incredibly simple, and they are called the master equations. And so as you can see that there can be mixings between, like familiar mixing between scalars and some particular polarizations of the metric fluctuations. So they will mix together. So in Kovtun-Starinets approach, they would mix with derivatives and things like that. And over here, notice that there is a box. So the box is for the background. And all the mixing is done at the non-derivative level. That's number one. And second, all the mixings are encoded in these mixing potentials. And those potentials, you can make them symmetric, okay? So this is some detail, but it's actually very convenient. And so it is the presence of this wave operator that allows you to actually prove the stability theorems in H equal 2 and H equal 1 sectors. And so it's very straightforward to extend the general proof that that's in Andrei Rostvorovsky paper, even in the presence of multiple scalars. So that statement is still there. So there can never be instabilities in any of those sectors. Good. So now let me go into some subtleties. So as you can see, so the formulas will be fairly simple and will be compact. And so this is an example of you don't need to pay attention to anything other than these red things that I will explain in a second. So what I want to say is that the formulas are simple in a way that there will be just some metric warp factors, and it's, and some, some potential and derivatives of the potentials that will enter in this master potential, right? So, but they will be very explicit functions. So you literally can take your favorite background, you plug it in, and you go ahead and compute the quasi-normal modes. So I did not present the formulas for the potential. So all the details will be in the appendix of my paper, so you can look at there. But there is a relation between the fluctuations in your background and these master scalars. Okay, so those are master scalars. And so the thing I want you to pay attention to is these things in the red. Okay, so when this thing in the red is 0, that means that there are some singularities. Okay, and so those are actually very, very physical singularities. So over here, you see K tilde, and I did not define for you what is K tilde. And so that's a definition of K tilde. So what's important is that these relations between master scalars and the fluctuations in your background, they become singular whenever K times K tilde equals to 0, and that's when L equals 0 or L equal 1 mode play a role, right? So again, what I'm doing right now, I'm discussing the helicity zero center, the helicity zero sector. And that's actually a physical thing. The reason is that when you talk about graviton fluctuations on the sphere and L equals 0 or 1, there are simply no physical graviton fluctuations. And so that's why you have to treat these harmonics in a special fashion, but it can be done. Yeah, so again, you can see either in some limit, well, I mean, you can look either in Andrei's paper or on my paper. Yeah, good. So I think I'm done with the general formalism. Are there any pressing questions, or I can move to actual application? No. Okay, very good. So now application, and just to demonstrate to you how easy it is. We have this general effective action, and now I'm going to focus on a particular model. So it's a holographic dual to a mass deformation of n equal 4 super Yang-Mills. And so you see, this is all I had to do. I just have a single scalar in this particular model. I call my scalar alpha. So this was scalar phi1, it's now alpha. It turns out that in this effective action, the kinetic term normalization is eta 1 is 12. I have an explicit potential. And this is a question that was before. Can I turn on, sorry, can I turn on the source term? And yes, you can. So you can see explicitly the source term. All right. So now the rest of my talk, which is about 11 minutes, as I can see, are going to be only plots. And so I don't know if I go through all of them, but let me see how it goes. So I have a background, I have all the equations I need. And so first, let me to identify, I'm looking now for thermal state. Thermal state with negative specific heat, okay? And so I am still in the regime when I have a black brane, so that I have translational invariant horizon. And so we know that in this case, the speed of the sound waves has to be negative, and we should see an instability in the hydrodynamic sector. So what you see over here in this model, I plot the free energy density. Okay, so that's just some dimensionless quantity. It doesn't really matter. Well, you know, if you are curious, so what I call, so that's just your free energy density divided by m to the 4th to make it dimensionless. And so what you see two faces. You can, it's a little bit hard to see here. So you see here the blue curve and you see a dashed red one. So the dashed red one is on the top. And so when I take the difference, so if I were to enhance it, so this would be, this is really ridiculous because I can use the red one. So let's see, where is this? Okay, so this is how the red one would look. And so when so this is really what I was discussing. We had this discussion regarding holographic conformal order. This is a metastable phase, right? So this is a phase that would have a higher free energy density compared to the blue one. And so over here, what I'm showing the difference between the two. And you can see clearly that this red dashed line is above the blue one. And notice this purple point. So this is a purple point where we will be doing all the quasi-normal mode computations. Okay, and so as I said, in this case, there is no curvature. Just to show you that this feature is robust, when you turn on the curvature, so in this case, I'm looking at exactly this model, when the curvature is of 4 as a mass scale, right? So K over m squared is equal to 1. And now you can see more pronounced this metastable phase, right? So metastable phase. Well, actually, this phase, because it's, I will show you in a second that it's this is the phase that would have a negative specific heat. And so again, you can actually plot this particular power 2/3 has to do something with the critical behavior of this point. Okay, and it's basically some mean field critical point. All right, so this is just exactly the same pictures in a microcanonical ensemble. And so this is, again, the answer to some of the questions that were asked before. Why do we care about those things? And so you can see here, so this is a transition point, right, in a canonical ensemble. And so you do care if you ask what would be the description of the system at energy densities below the one at the critical point, and that's, you are in this sort of funny phase with a negative specific heat. Okay. Now I'm obsessed with checking my numerics, and so this is basically, and before I start showing you some answers, what happens with the quasi-normal modes, you know, I wanted to make sure that I really understand my background. So this is a numerical check of the first law of thermodynamics. So if it is equal to 0, then my first law is 100% satisfied, and you can see that we are at the level 10 to the minus 10. And so I have control over my numerics, both for black brains and black holes. So now we can look at actually hydrodynamics, right? So I can compute the speed of the sound waves, and I can compute, for example, bulk viscosity, and so this is our purple point, right? So this is a point that we will be computing our quasi-normal modes, and I have chosen this point so that I am in a dynamically unstable regime. So one curious fact is that you can see that, for example, at this point, because the speed of the sound squared is equal to 0, the specific heat is inversely proportional to the speed of the sound, and it actually diverges something like T minus T critical to the power minus 1/2. So the bulk viscosity is finite here, okay? So bulk viscosity is finite at criticality. But it doesn't mean that all the transport coefficients at this funny point is finite. So for example, if you were to compute the relaxation time, you will find out that the relaxation time diverges. And this is something that I believe David Mateos in some of his talk was mentioning as well in his model. Good. So now, so the next thing that I want to do, I want to compute the hydrodynamics, right? So I'm going to look at the quasi-normal modes of the system, and so what you see, I don't know. Okay, good. So I can enlarge here. So you see these dashed lines, and that just comes from applying this formula. Right? So those are dashed lines. And so this is a very good check that I have a good control in the computation of the quasi-normal modes, and it agrees with what we expect from hydrodynamics, because I don't really need quasi-normal mode techniques to compute the speed of the sound waves or to compute the bulk viscosity. I can extract it directly from the background, all these quantities. And so what do you observe? You observe that there is really an unstable range, right? So this is an instability in your quasi-normal modes, right? So you're in this range there. The imaginary part of this quasi-normal modes is positive. And so what you need Q to be larger than some Q critical. So this is your Q critical, so that you stabilize the energy pressure fluctuations along the extended horizon. Now you can actually see this interesting feature. So first of all, now when you do explicitly computation, you see that these funny quasi-normal modes are purely imaginary, right? So the real part of their frequency is equal to 0. And so this is the one that's unstable. Remember, there were two signs here. Right, so there are two signs here. So for imaginary speed of the sound waves, one is stable, the other one is unstable. And so that's exactly what you see here. One is stable, the other one is unstable. And they join together once you start increasing Q at some point. And then at that point, they actually develop real part. Okay, and so the green quasi-normal modes that you see is just basically an extension of this. So you can see that the portrait of the quasi-normal modes is kind of interesting. Now I see I have only 1 minute left, and so I'm going to scroll down, and you can do lots of computations and observe lots of interesting things. With quasi-normal modes when you start curving the horizon. Unfortunately, I have to skip all of that.
Hey, Alex, I think as a co-host, I think you had plenty of questions, so you can take 5, 10 more minutes.
I don't want to abuse you guys. I don't want to abuse you guys, and but I wanna highlight the interesting things. So I'm really taking effort to write this paper so that you don't need to read all the technicalities, and you will be guided into exactly what is done. And so hopefully in a week you will see the details. So let me highlight the difference. Okay, so I told you that, and you can see this going back to David Mateo's question. What do I mean by hydrodynamic mode? You will see the intricate interplay between hydro and non-hydro when K is not equal to 0. So here what I am plotting, so I have to fix this, in principle you can do it at any state. So I fixed a particular state. So I keep the temperature over mass fixed. And I picked it in unstable phase. And so again, remember that instability is in the hydro. And so when I look at L equals 0 or L equal 1, so those are the fluctuations that do not involve the graviton. And so those are non-hydro. And so what I am doing, I'm exploring how my quasi-normal modes changes as I change the curvature of the horizon in a smooth way. And so those 2 points, that's where k is equal to 0. And so you can see that initially, those are the non-hydrodynamic modes and they are stable. Okay, so those are the non-hydrodynamic modes which do not have a real path. And it's an interesting story, actually. It's an interesting story to ask. How does it come that you have quasi-normal modes which do not have a real path? And this is what I skipped. Okay, so you start, you can actually follow those modes as you change the mass, right? So everything starts with both real and imaginary path, and you can follow them how to, you know, to the mass that you need, and you will find out that there is an interesting thing happens with the quasi-normal modes, and so the branch that had real paths collapses, and you develop 2 branches that have only imaginary path. But the important thing that I want to say is that when L equals 0 or 1, those modes are stable. And now see what happens as I increase K. As I increase K, what I discover, and this could not have been foreseen, that there is an instability that develops. So initially, some of the non-hydrodynamic modes, as you start curving the horizon, they become, they started as being stable and then they become unstable. And then if you curve it far enough, they become stable again. Or better yet, they just disappeared. Okay, you can see. So again, when you do your numerics, you actually follow them against this thing. And it's really cute that they actually join in this particular fashion. Okay, so I view this as a highly non-trivial check that that what I'm doing makes sense. Now, those things are also interesting. So you can zoom in and you can see that there is some interesting, intricate dance that the quasi-normal modes are doing. So now, let me talk about the. So I am already abusing you 3 minutes, and I promise you 2 more minutes, and we're done. So now I want to discuss the fate of the sound instability. Okay, so sound instability. And so what you would expect that, so your sound was already unstable at k equal to 0. And so it will continue to be unstable if k is sufficiently small. Okay, and so then you would hope that the instability will be cured. And so this is exactly what you see, right? So this is at k equal to 0. And so this is something that was an unstable branch of your sound. And so you see that that it starts being unstable. And then there is some critical value of k, curvature of the horizon, when I am stabilizing this branch. And then I can follow it again. And so that was, okay, so let me just say, so this was hydro. This is hydro at k equal to 0. And the magenta dots, the 2 magenta dots are non-hydro. And so you can see that the way how these quasi-normal modes behave. Remember, there were 2 branches of the sound. One was unstable, and the other one was stable. So this is unstable, and this was what was a stable branch. And you see that as you start changing the curvature, so the stable branch actually connects with the stable branch that originates from the non-hydrodynamic mode. And then again, there is this coalescence of 2 branches. So those are the branches that have only imaginary part, and then you get the branch that has a real part. And so what I'm saying is that there is a very interesting picture. There is a very interesting picture that emerges exactly how you cure the instabilities if you start with the extended horizon and you start putting it on a sphere. So something very interesting is that you see that I cured the instability in L equal 2 sector at some value of the curvature, and it turns out that at this value, L equals 0 and L equal 1 are still stable. So they become unstable for k over m squared larger than 0.052. Okay, so what this means that there is actually a stability gap in some intermediate range of curvatures where you already fixed the instability. You thought you already solved the problem. You fixed all your problem in the, what was your sound channel, but you were wrong, because something that was stable will become unstable at a little bit larger instability. And you can look also at modes at larger L, and as you might expect that, so first of all the modes will become unstable. It's easy to understand why. And however, you're gonna cure those instabilities at small and smaller values of k. Good, so let me go to my conclusions. So I reminded you that extended horizon can have crumpling instability. And so this crumpling instability can be stabilized by positively curving them. And so this is something that that I tried to convey to you, that there is a very intricate pattern exactly how the stabilization occurs. So I did not find any instabilities in L equal 1 sector. So there were instabilities in L equal 0 sector, which were very unexpected. And then there were expected instabilities in L equal 2 sector. So those were instabilities from the deformed sound waves. Yeah, so now once I know that the framework works, I reproduce lots of old results, because there is a lot of results in the literature on hydrodynamics of n equal 2 star. So I can ask the question, what happens with compactified conformal order? I can go back and look at stabilization of Klebanov-Strassler black holes. And so there are some interesting things that happens exactly how this instability is cured, and you might be interested to know which aspects of this stabilization are universal and which ones are just, you know, the reason you looked at a particular system. All right, thank you so much.
Yeah, thank you very much, Alex. That was very exciting. And you already know from the feedback of questions that you got. But yeah, so are there more questions? I bet there are.
Yeah, I have a question, Alex.
Yep.
Coming back to something I tried to ask at the very beginning. So if I understand correctly, all the instabilities that you are trying to cure are infrared instabilities, in the sense that they appear at low k and they disappear at sufficiently high k. Is that correct?
That's what I would have thought before. But see, that's the thing, that's, you know, this L equal 2 instability, it's not an infrared instability. So I would have thought exactly as you. That's sort of the normal expectation. So it's an infrared instability. I start curving the thing, and if I curve it enough, it will be cured. And so over here, what happens is that so those are the non-hydrodynamic quasi-normal modes of the planar horizon. And I just follow them, what happens with them. So those are the modes with L equals 0 in this particular model. And I just follow what happens with them as I start curving the horizon. And as you can see, that they become unstable. So there is this, I do not have a simple physical reason why this instability arises, but there is, so this is an instability of the, you know, black holes. Without a simple physical reason why it should be there.
Yeah, so I guess I appreciate this. What I was trying to get at is because in this case, these modes at k equals 0, capital K, I mean, at 0 curvature of the horizon are stable.
Yes.
So what I wanted to ask is the following. Suppose you start with a model that with a flat horizon has some instability that you would like to cure. for a flat horizon, if I understand correctly, the instabilities are always infrared instabilities.
Correct.
So wouldn't a simple way to cure them be simply to declare that they still live on a flat horizon, but you periodically identify it on a torus, so that you impose an infrared cutoff by putting it on a box instead of on a curved sphere?
Yes, that's a simple solution. That's correct. As surprising as it is, it never occurred to me. Normally, I wouldn't like holographic models with a torus, right? So that's what you were saying. But okay, so one of the reasons that might be the case, it's not the reason I'm saying but the reason why you might worry is that when this torus would shrink to zero size, right? So that would be that would be like a deconfining. Sorry, that would be like confining phases of your models, right? With the torus size shrinking to zero size in ADS, and I don't see anything wrong with that, right? And that's, as you pointed out, that would be a way to cure the hydrodynamics. The thing is that in those cases, there will be winding strings, right, that you start worrying about. And so you are out of the, supergravity approximation. But I haven't thought about your question. So obviously what you said a more straightforward way how you cure the problem, right? So you just impose a symmetry on the problem where you cross out the states, the unstable states, right? So the torus periodicity will cut off K, and I can always cut it off. So I can go back to, say, this picture, right? So this is a picture of K equals 0. And so all I have to do is just to impose the periodicity so that the lowest mode on the torus is over here. So you will still have, the thing is that you will still have a K equals 0 mode on the torus. But it's probably, so you have to be a little bit careful. So I don't want to say right away that you are completely safe, but it's possible that you are safe. So the only ones that you will have is K equals 0, the homogeneous mode, but maybe that's okay. Maybe it's like a pure gauge or something.
Yeah, I think in the cases we looked at, also related to this sound mode instability associated to negative specific heat, if you put the system in small enough a box, it becomes stable.
Yeah. So that's again, this is just oops, sorry. So this is really this feature.
Yeah, thanks.
Yeah, thanks.
So can I also ask a question related to David's question?
Please.
So if you can introduce the cut of like torus compactification and cure the instability, do you think this instability is related to the Gregory-Lafflamme instability?
Right. So in some sense, these instabilities are like Gregory-Lafflamme instabilities, right? So you see that they're so this is exactly what David was talking about, right? So this is the instability that has finite range and momenta.
Looks like we may have lost Alex.
Yeah.
I'm going to pause the recording. Right. In the absence of our speaker, I would like to still thank you for participating and Alex Buchel for giving the talk and concluding this recording.